So last time you guys, you guys, I think I asked you to do stuff, right? Yeah. So would have been like the 13-1 homeworks, and then this worksheet 1, right?
Yeah.
How did this go?
Easier in the back. The back was lower.
Looks like this direction people are missing. Yeah, Nicole.
I didn't know how to
As you go.
Hey, can you guys stop talking on top of other people so I can hear the questions that people are asking right now? So unless you're trying to comment about how the homework went, I'm not really interested in it. Thank you. All right, Nicole, let's try one more time.
I didn't know how to do the sketch for the side.
Okay, so so the sketch should come from just your calculator.
Yeah, it gave me like an error when I tried to.
Interesting. Okay, so you and I just need to take a look at what's going on with the calculator a bit later, which is fine, but that's all you're really doing there. It's just doing the draw option on your calculator to draw the picture. Which again, like, if the calculator's functioning correctly, is easy to do, right?
Yeah.
Okay, that's fine. Emerson?
On my Notre Dame, it says it's due this, like, on the Sunday.
Great.
So can we just turn it in?
Or you can turn it in like, I was gonna collect these and look at them, kind of thing. So if you're done and you wanna get rid of it, that's fine, you can turn it into the folder before you leave today.
Is this the homework? Or is it like?
In class assignment.
Oh, we did this.
Yeah, that.
Oh, we did that.
Oh, I thought you were talking about.
We're talking about the worksheet 1. 1 through 4 was not due on Sunday, it was due this following Sunday.
Got it.
Yeah, we did the
I
tour.
thought you were
So if you're done on that, that's fine. This guy, we're here to, eventually we'd like to collect and look at, but if you're still finishing, that's fine, it doesn't need to be done this second. Is everybody okay? So t-test we feel comfortable performing, setting up and performing and interpreting? To some extent anyway? Done a fair bit of practice on that now. And you guys went through the second half of the PowerPoint and looked at how to do it on your calculator with raw data instead of. Okay. But you looked at how to do this with raw data instead of means, right?
Yeah.
Yeah, okay. Good. All right, we're gonna do part of 3-2 then today. But I'd like to stop a little early and you have a chance to talk to some people about their talk to them about their IA stuff. So if you've sent me an IA submission, unless you did it this morning, I've looked at them and responded. Some of you may have gotten something as simple as like approved. Some of you might have gotten like, well, I think this is a good idea, but you need to give me like a real proposal. Some of you might have gotten like, I don't think this is gonna work. Here's why, or like this is not like this is an appropriate topic, and here's why. Although some of you guys were like, I think on the right track for something, some of the ones that I rejected, but hold on a second, because I think we lost one out here leaving anyway.
That's a lot of people.
All right, Jamie Brooks.
I might not know.
What college?
Drop this off. It's on the way there, saying that she'd already was on.
I saw the question.
I bet
I'm gonna definitely class.
I might apply it.
All right, so The other, alright, where was I at?
From I talked.
Oh yeah, I topics. So some of you guys might have been close and just like, either you need to do some tweaking to make your variables something that are more measurable, or you have a kernel of an idea here, but like what you're setting up, it just seems like way too much work for me to feel good about you trying to undertake. Yet again, when you're writing these things, you need to think about like, where is this data gonna come from? So either like, hey, I already know there's a pre-existing data source for this where I can get raw data. Like Jamie sent me something that looked pretty good, and I looked, and there's like no raw data available on the link that she sent me. It's like, well, this is already categorized. I don't know if you can do anything with this. Which again, like, cool idea. If you had the raw data, oh, sorry, Quinn, I meant. Did I say Jamie? If you had the raw data, like, wonderful, I think would work great. But without the raw data, I don't know what to do with that. And maybe if you did like a ChatGPT and asked it to find the raw data for this, maybe it would find it. Like, I'm not saying that it doesn't exist, it's not publicly available, I just don't know where to look for it. So unless you have like gone and found the public, like a public database to get the data you're talking about needing to collect, or you have something that your peers would self-report on, that's easy for them to self-report on. Like somebody was wanting to look at like shoe size and vertical jump. Like, well, I wouldn't trust any of my classmates to report on vertical jump, which means you have to be measuring, like 50 plus people's vertical jumps. Probably more work than I'd want to be doing, because I don't know that you have a setup to do that. So like, probably do something else, but like, cool idea, like nothing wrong with that. But it's like one of those in principle, or some people were doing like a qualitative variable, like somebody wanted to talk about like whether you listen to music or not when you're studying. I'm like, well, that's qualitative. It's like a yes or no, music or no music. It's not numeric or quantitative. Or even stuff that seems quantitative that's really not. Like somebody want to look at grade level associated with something. It's like, well, I know it's like 11 or 12, but it's really just a qualitative functionally, because it's one thing or the other. Might as well just be a label. It's junior, senior, then it's definitely not quantitative, so I'm gonna leave a little bit of time here at the end to, I know some people I emailed specifically back about like, yeah, I'm not sure about this, but there's something here, maybe we should talk about this. So I wanna carve out some time for those people. Everybody okay? So today, we're gonna talk about another type of hypothesis test. This other type of hypothesis test is called a chi-squared test. There's two versions of this test that we'll talk about in this class. There's a goodness of fit test and a general chi-squared test. Today we're going to be talking about the goodness of fit version of this test. Okay? So we're still just, in this chapter, we're going to look at three types of hypothesis tests. The t-test is what we've been talking about. The chi-squared goodness of fit test, and then just the standard chi-squared test. So the chi-squared goodness of fit test basically is going to analyze whether our sample fits some known distribution. So like, you are, you're a company that manufactures like screws or something. And you're building like, you just manufacture the same like, 3/8 diameter, like 2-inch screws or whatever. Okay? And, you don't get exactly 2 inches because nothing's exactly anything, right? Like you expect that like 90% of your screws are between like, 2.05 and 1.95 inches. right? That's your criteria that you're trying to manufacture to. You sample and you wanna see if like the distribution of screw sizes you're actually measuring, that you pull off the assembly line meet, what your engineers that design the assembly line say you're supposed to meet, right? Like that's a goodness of it. Does that make sense, kind of thing? Or if you're talking about like, you have like all these different colored candies, right? Like M&Ms or Skittles or whatever. Like the amount of colors in each bag is predetermined, right? Like we're gonna make, like 13% of them are gonna be brown and like 26% are gonna be yellow and whatever, and then they all kind of get mixed together and dropped into the bag. You could test to see if the distribution in the bag, if they're doing a good job of mixing, actually meets the known distribution. Like I know there's this many of these things. To see if they're really like randomly mixed together in their big vat before they drop them in your bag. But that's the idea. The other version of the chi-squared test is going to check to see if one variable has an effect on the other. That's the general chi-squared test, or the chi-squared test for independence, to see if two variables are dependent on one another or independent of one another, whether there's a cause and effect relationship, or at least evidence for a cause. It can't have actually determined if there's a cause and effect relationship, but evidence to support that notion. Is everybody okay? Those are the two types. So one, are we seeing if like our observation fits some known information? And then the second is going to test to see if two things like have a cause and effect kind of relationship with one another. That's the kind that you'll probably be doing in your IBA. Since we're picking two variables and trying to test to see if they have an association, right? So let's look at an example. So Mars Incorporated makes milk chocolate candies. Here's what the company's consumer affairs department says about the color distribution of its M&M milk chocolate candies. On average, the new mix of M&Ms will contain 13% brown and red, 14% yellow, 16% green, 20% orange, and 24% blue. The two-way table summarizes the data from a sample bag of M&Ms. In general, one-way tables display the distribution of a categorical variable for the individuals in the sample. So this bag of M&Ms that we opened had 60 total M&Ms in it. 9 were blue, 8 were orange, 12 were green, 15 yellow, 10 red, 6 brown. It was okay with how you read the table? How many categories are in this table? 6. Why 6? Anthony? One for each color, right? The color is the categorical variable. Everybody's okay with that? There's 6 different colors listed, 6 different categories. So for example, if I was looking at the sample proportion of blue M&Ms, 9 out of 60 were blue, so like 15% of the M&Ms from this bag were blue. Is everybody okay with that notion? And we could do the same thing then for orange, green, yellow, red, brown, etc. Since the company claims that 24% of all M&Ms are blue, we might think that like, hey there, 15% is a lot less than 24%. Maybe there's something funny going on here. Are we losing blue M&Ms somewhere? Is this just not mixing well in their giant mixing machine before they spit these M&Ms out into a bag? What's going on here? You could do a one sample t-test to test these hypotheses, right? So the null is that the sample proportion is actually 24%. The alternative is that it's not. 24%. And then we could repeat the same t-test calculation then for oranges and greens and yellows and reds and browns. Seems exhausting, doesn't it, right? Alternatively, rather than doing 6 separate t-tests, one for each color, we can do a 1 chi-squared goodness of fit test and kind of knock all the colors out all at the same time, which is usually the preferable option here. So that's what we're going to be talking about, is this goodness of fit test. So the null hypothesis in your goodness of fit test is that the stated color distribution for M&Ms is correct. I.e. that means that the color distribution matches the company's advertised color distribution. The null hypothesis for all chi-squared goodness of fit tests is that the sample matches the known standard. Whatever word it is we're talking about, you work in to like M&Ms or pets or whatever you're talking about. But it's always that it meets or matches the known standard. Is the null hypothesis, is that everything is good. The alternative is simply that it does not match the known standard. In the case of M&Ms, that the actual color distribution doesn't match up with the known color distribution. It is, very unlikely that the sample we took would have this color distribution that we found. That it's probably more than just bad luck. There's probably something in the manufacturing process of these M&Ms that's not mixing these things well enough to where we're getting the sample distribution we're advertising. Is everybody okay with kind of conceptually what we're doing here? So the goodness of fit is going to sound very much like a t-test setup, but it's going to have, instead of just having one t-test, this would have like multiple t-test setup, is the way it would read. Is everybody okay? So, I could also write these hypotheses symbolically. So to say that the sample matches the known standard means that the probability that we're blue should be 24%. The probability that we're orange should be 20%. The probability that we're green is 16%. And so on and so forth. And the alternative is that at least one of those probabilities is incorrect. Yes? Is everybody okay with that? Saying the same thing as the previous slide did, this time symbolically instead of in English. Which one do you suppose you prefer to write? Probably the English language one. It's usually a lot less writing. To just say that the sample matches the known distribution, or that it, and the alternative is that it doesn't. So, to do a chi-squared test, any chi-squared test, we have to compare our observed counts, that is what we actually found in the sample, with the expected counts, that is what we would have expected to get had the sample actually matched the known distribution. So the observed counts will be given to you, like that's the table of data that you got at the start. The expected counts is something we'll have to calculate. So to do that, to calculate our expected counts, we had 60 total candidates, right? So for example, we're told the blue M&M should be 24% of our bag. So we'd expect 24% of those 60 M&Ms in our bag to have been blue. So if I do 0.24 times 60, I get 14.4. That would be my expected count for blue M&Ms. Is it okay to have a decimal here? Absolutely. Expected counts don't need to make sense based on the thing that you're talking about. Is everybody okay? Easy calculation, right? Just take the known probability and multiply it by the total in your sample. So we've done that for blue. We'll do the same thing now for each of the colors based on the known distributions. Again, where did the 24 and 20 and 16 and 14 and 13 and 13 all come from? It was given to me in the original statement of the problem, right? That was what the Mars Corporation advertises as the proportion of colors in of M&Ms. So far, so good? So if I put that into a table, I have my observed counts and my expected counts side by side. Quick eyeballing. I don't know, they look a little different to me, but maybe not different enough, right? That's the question, is like, how different are they? Is it different enough so that the odds are that this was just like a crummy sample? The odds pretty bad that that was just all it was? I don't know, it's hard to tell by looking at it, right? We need to do a little bit more. So what we're gonna do, again, here's like another visualization of comparing the observed and expected counts with a bar graph, like what did you do? From the bar graph, it looks like there's some fairly large discrepancies, but is it large enough to say that they're actually different? That's really what we're trying to get to. The way we're gonna make that decision is using what's called the chi-squared statistic. And we'll show you how to calculate that here in a moment. So the way to calculate the chi-squared statistic, the chi-squared statistic is the sum of the observed count minus the expected count squared divided by the expected count. And we sum those up over all our possible categorical variables. So how many of these little fractions would we be adding up in the case of our M&Ms? 6 of them. One for red and green and blue and yellow and orange, brown, I don't know what colors anymore. Is everybody okay? So depending on the size of your data, this is realistic that you could type out into your calculator by hand, right? If all I have to do is type in 6 fractions added together, that's not terrible. It's not great, but it's not terrible. There's only 6 of these things. Doable. Doable to do by hand, right? This would be something in a small enough problem that I would expect you to be able to show the work by hand. Right? We'll show you how to do it on the calculator also, don't worry. But I want to point out to you that this particular calculation of writing like 6 fractions added together and then doing the addition with your calculator would not be terribly tedious. A little tedious, but not terrible. Okay, so here's our table of observed and expected counts. So I'm going to go ahead and take observed minus expected, quantity squared, divide by expected, for each of the categories, and then add up those fractions. Let the color coding move here. Really pop this on. So when I do that, I end up getting 10.180. That's my chi-squared statistic, is at 10.180. And again, that's like a measure of distance of like how far my observed count is from my expected count. I mean, the bigger that number is, typically the more deviation you have from what you'd expect, but is 10.8, is that a big number or a small number? We don't really have a sense of scale here, right? Like, what's up?
I was gonna ask, like, when do you know if it's like a little bit too big or too small?
Yeah, we're heading right there. That is exactly the right question. Because that's, again, it's like, okay, that's just a number. It's like, is 10 a big number? Is it a small number? I don't really know. If I'm expecting to get like 0.7, 10's pretty big. If I was expecting to get 1,006, 10's pretty small. Like, what are we really talking about? What should I be comparing this to? So what we're gonna be looking at is, we're gonna do something similar to our t-test, right? So in the t-test, we had that t-distribution. We found where the t-statistic was on that distribution. We looked at the amount of area under that t-distribution curve as a probability and compared that to our level of significance, right? That's essentially what we did. We're gonna do the same thing here, except we're gonna use a chi-square distribution. Now, there's infinitely many chi-squared distributions, oh no. And depending on the degrees of freedom, the shape of that chi-squared distribution is gonna change each time. The calculator will handle all this part for you, don't worry. But if you're doing this by hand using calculus, these things. So the thing that determines the shape of our chi-squared distribution is the degrees of freedom. That's just the number of categorical variables minus 1. So if you think about it, you have 6 categorical variables, right? 6 colors. The first color you have, how many choices to pick there? 6, okay? So you use that color, now how many choices do you have? 5. And then, no. 0. Because you don't have a choice for the last spot, right? If there's only one thing left, there's no choice. It's just decided for you. Degrees of freedom, how many choices you have, total number minus 1. So you have 1 choice for the first out of 6 things, 1 choice for the second, for the third, for the fourth, for the fifth, and then for the last, there's no choice left at all. Because you have only one thing left, it has to go there, there's nothing else. Does that make sense? So that's all we mean by degrees of freedom. So what I have here is a picture of some of the different shapes of chi-square distributions based on their degrees of freedom. So there's a 1 degree of freedom, a 4, and 8. Does this really matter to you? I'm just pointing this out to you, like, if you hit the draw function on your calculator, you're like, why does the graph look different every time? It's because it depends on the degrees of freedom on the shapes. So again, not germane to doing this, but I want to mention it just so that when you look at the draw function on your calculator, you're like, I don't know if I'm doing this right, but every time the picture seems different. Am I doing something wrong, Mr. Kulik? No, not necessarily. So the last thing, and it's a big thing, is that for us to have a valid chi-square test, for us to use this calculation and have it actually, us be able to say that it means anything, 2 conditions have to be met. 2 conditions. And you have to check those 2 conditions. The first condition is that the sample isn't too big. That's called the randomness condition. And your sample can be no more than 10% of the total population. Okay with that? So remember the example we've been working with M&Ms? How many M&Ms were in our sample? 60, right?
60.
If 60 was 10% of all the M&Ms in the world, how many M&Ms are there in the world?
600.
600. Are there more than 600 M&Ms in the world? Well, obviously, Mr. Kulik, I've eaten at least 600 of them in my life, you know?
Those technical areas.
Everybody feel good about how we can verify the randomness condition?
Yeah.
You can just show that, like, hey, if this was 10%, that means that's all there is in the world, and like, that ain't all there is in the world. Does that feel good? The second is called the large counts condition. And for the large counts condition, you need to make sure all your expected counts are greater than 5. Do you remember our expected counts on this one? Do they all make that?
Yes.
Yeah, I think if we go back and look here real quick. There we go. Look at our expected counts. The smallest expected count is 7.8, which is bigger than 5, right? Do I need to compare each one of them to 5? No, just say the smallest expected count is this, and that's bigger than 5, so we're good. Right? Do it in the most efficient way possible. All right. So just like in a t-test, we're going to compare our chi-squared test, or use our chi-squared statistic to calculate a probability to compare to a level of significance. We're not going to actually calculate that probability. Oh, no. Calculator does that part for us. I never ask you to do that by hand. It's coming up with the chi-squared statistic itself. Fair. Calculate the probability. No. Not fair. Again, the level of significance, we denote that with the Greek letter alpha. It's just some standard that says, okay, this is the, anything that's like 5% or less, that we could have gotten this, the probability is 5% or less, that we could have pulled this sample just by bad luck. Is that enough to say that this is, that these two things are actually different? For something like proportion of M&M colors, I would be comfortable at 5%, right? If it's medical, and it has to do with like whether I'm gonna live or die, 5% feels a little risky to me. So again, level of significance is arbitrary to the situation and what we think is an acceptable amount of risk that, really these two things were not different. They were really kind of the same thing. And we just pulled an unlucky sample, right? That's kind of where we're at. Does everybody feel okay? Same ideas with the t-test, right? All right. Alternatively, you can compare your chi-squared statistic to what's called a critical value. So the critical value is the chi-squared statistic that matches your level of significance. So like if I look at 5% under the curve, that's going to correspond on the x-axis to a chi-squared value. And then I can compare that chi-squared value to my chi-squared statistic. It's just another way of doing the same thing, right? So, can I just draw in here? I think I can. Yeah, cool. So like, let's say that's our chi-squared statistic, right? Let's say that this is 5% of the area. So that number is chi-squared 5%. Everybody's okay? That's our critical value. Yeah, absolutely. If it's time to go past people, you hit it. Is everybody okay? So if my chi-squared statistic was greater than that 5%, that would mean we'd be over here, right? Is the probability over there going to be bigger than 5% or smaller than 5%? Smaller, right? So a bigger chi-squared statistic in comparison to the critical is the same as a smaller probability than the level of significance. It's like the inequality directions are reversed. Is everybody okay with that idea? Again, the picture makes all the sense in the world when you draw them down about what you're talking about. So again, like, this is my level of significance. That's my chi-squared statistic, and then like, that area over there would be like my p. Does everybody feel okay with the picture? I think that's... Sure. I don't know how to get a different color. I would do that. Okay. So this is like that's like my alpha, right? That's my level of significance. That area is 5%. So this x value is my chi-squared critical value, right? My chi-squared statistic, say, is here. So this area then is my P. Notice that when P is less than alpha, implies that chi-squared critical is greater than no, I have that reversed. Chi-squared is greater than chi-squared critical. Right? Emerson, do you see it now?
Yeah.
Right, because this is further to the right on the x-axis, so it's a bigger number, but the area above it is smaller because there's less of it.
Got it.
Cool?
Yeah.
Okay. Again, the picture kind of sums it up pretty nicely. You just have to know what you're looking at. But it's the same idea, right? So again, it's just a different way to skin a cat. You don't know that phrase?
Crazy saying.
Is that offensive towards you? You have cats.
I do cats.
Thanks for sharing. All right. So again, our rule for deciding whether to accept or reject our hypotheses, if we're comparing the chi-squared statistic to its chi-squared critical, we say that we reject the null hypothesis if the chi-squared is greater than chi-squared critical, which means that it does not, the sample does not match the known distribution. But if chi-squared is less than chi-squared critical, that means that our sample does fit the known distribution. Meaning the probability that we got this sample, was greater than the 5%, right? Anthony, you're okay? It's the reverse of what you'd expect with p's and alphas, right?
Yeah. Oh, okay. So what's the difference between chi-squared and chi-squared critical?
Chi-squared is the one you calculate.
Yeah.
Chi-squared critical is the one based on the level of significance. So chi-squared critical would be given to you in a problem,
Okay.
right? It would be like compared to this chi-squared critical level.
If it was just, like, is there a way for it to just be equal to, like, it wouldn't be less than or equal to, like,
Well, less than or equal to includes equal,
okay, so
right? So if they're the same, then it's, if the two numbers are the same, then we say that it fits, fits the known distribution, yes. Is everybody okay? So again, here's that same picture I drew. So I have my chi-squared value and my corresponding p-value. Remember, the p is this area under the curve. There's the chi-squared we calculated. This is the 5 degree of freedom chi-squared distribution curve. And if I go and I look up on my table for chi-squared with 5 degrees of freedom, and I have 5% level of significance, the chi-squared statistic is 11.07. When I was a student, that's how we had to do this. We looked it up off of table. Your calculator can probably produce that somehow using like inverse chi-squared distribution or something. I would never ask you to do that. It would be given to you in a problem. Which is right over here somewhere, right? So since our chi-squared is less than our chi-squared critical, that sample fits the known distribution. We accept the null hypotheses that, okay, that's good enough. Chances are that pretty good that this was still the same thing. Alternatively, when you use a p-value to do this, same way we did for t-tests, good? So it's the same idea. Where does the p come from? Do we calculate it by hand? Never. It's always going to come out of the calculator. Never p-value by hand. Very good. So if this was like no calculator kind of test, you'd be getting a chi-squared critical value to compare to your chi-squared statistic, because realistically, if the numbers are not too disgusting, you could do the chi-squared statistic by hand, right? Because all you have to do is like add, subtract, square, and divide. If the numbers are not terrible, that's realistic to do. I would never ask you to do something with no calculator. I'm just talking about like, why do I need to know both ways? Because you can. Why climb the mountain? Because it was there. As previously mentioned, there are two conditions that should be checked before any chi-squared calculation begins. Because if either of these things fail, there's nothing you can do. Your chi-squared statistic is meaningless. So the randomness condition, the data is given from a well-designed random sample, and 10% of your sample is that your sample is no more than 10% of the entire population. So randomly chosen, not too big. And second, all expected counts are greater than 5. Notice that's a hard greater than, not or equal to. Gotta be greater than 5. Always do this before any of either of these fail. You stop and say that the sample is not appropriate to be analyzed using a chi-squared test. Everybody's good? I want to point out to you, even though an expected count, or even though an observed count can be less than 5, your expected count still can be greater than 5, right? Easy to see that, even if I got no orange M&Ms in my bag, 12% of 60 is still, 13% of 60 is still greater than 5. No big deal. All right, to summarize what we do. So first step, suppose the two conditions are met. We check for randomness in large counts. And then to determine if a categorical variable has a specified distribution in the population of interest, we expressed as the proportion of individuals falling into each possible category. We state the null hypothesis that the stated distribution is correct. The alternative is that the stated distribution is not correct. We then calculate an expected count for each category by assuming the null hypothesis is true, and then calculate the chi-squared statistic using the formula given, and then compare either the chi-squared statistic to its corresponding chi-squared critical value, or the calculated p-value compared to the level of significance. We'll do this example here in a second. So this is just the kind of the overview of the steps. I don't need to save that picture. I'm not going to do it. Sorry if you're like, oh no, I was counting on that picture you drew. The same picture's in there later, basically. Of course. Actually, I just want to stop here. We'll do the in-class examples later. I want to give a chance to talk to some people about IA stuff if I emailed you about it, or if you have questions. Some of you haven't submitted anything yet. Shame on you. Get on that.
Shame on you.
Shame on you.
Well, before